Welcome back everyone. In the last lesson we learned about simple linear regression or least square regression. In this lesson we are going to learn about an extension of that regression, which is the polynomial regression and multiple linear regression. Polynomial regression refers to fitting a higher order polynomial. A higher order polynomial means a second order curve, that means a parabola or a third order curve, something like that. And multiple linear regression means if we have more than one independent variable, that means if say for example we have a function that depends on two independent variables like x1 and x2, so in those cases that applies the multiple linear regression. So in this lesson we are going to learn about these two special type of regressions. So let's move on. So in this case, we are still going to fit a least square definition, a least square criterion. So if you remember from the last lesson, the definition of the least square regression was that you need to minimize the summation over the error square terms. So that was the definition of the least square. So in this lesson, we are going to similarly apply the same criterion. That means we need to minimize the least square error. But in the case of polynomial regression, how we are going to do that? In the last lesson we fitted a straight line, that means a linear regression line, and the equation was a0 plus a1x. But in this case we are going to fit a polynomial regression. Let's say we want to fit a second order polynomial, and that makes the error as a0 plus a1x plus a2x square. So this is the polynomial regression equation, a0 plus a1x plus a2x square. So this is the fitted polynomial regression line. But to get the original value of the data points, that means y, we need to add the arrow term, individual arrow term with each of the fitted point. That means a0 plus a1x plus a2x squared, this is the fitted polynomial regression line, and we add the arrow term with each of the points. As a result we will get the true value. So if you remember, the arrow term is denoted as the difference between the true value and the approximated value. So if we just algebraically manipulate this equation, we can get the arrow term, which is y minus this whole term, y minus a0 minus a1xi minus a2xi square. So this is the difference between the true value and the approximated value. So this is the error. So if we just take the square of each of these error term, so this is the square term, so that makes the error square of that individual point, and then we sum over all of the data points. That means I equal to 1 to n. So for all of the data points, for n data points, we get n error square terms. We take the summation and we get the total summation over the square error terms, which is denoted as SR. So we need to minimize this SR term. So similarly, in the similar to the case of linear regression, we are going to minimize this SR term. So what we are going to do, then there are three individual parameters that are going to be determined, a0, a1 and a2. So we need to determine these three parameters, a0, a1 and a2. These are the characteristic parameter of the fitted polynomial regression line. So we are going to just differentiate this SR term with respect to a0, a1 and a2, similar to the case of linear regression, and then we equalize these equations equal to 0. For example, we differentiate delta SR with respect to a0, that means delta SR divided by delta a0, which makes these equations look like this. Okay, similarly delta SR divided by delta a1, delta SR divided by delta a2. So all of these differential terms is going to be 0. Why? Because we want to minimize these arrow terms. So differentiating with respect to any of the characteristic parameter of the regression line is going to make these arrow term equal to 0. So delta SR by delta a0 equal to 0, delta SR by delta a1 equal to 0, and delta SR divided by delta a2 equal to 0. So if we do this, we will get the three equations which look like this. Okay, then we just algebraically manipulate these three equations and we get these three equations from the differential equations in the last slide. So if you just work this out at home, you will get these three equations. So what we want to do, we want to determine these three parameters, a0, a1 and a2. So we have three equations and three unknown parameters, so we can easily determine these three parameters. Okay, So you already know how to determine these individual coefficient terms. This n equal to the number of data points given, summation over xi, summation over xi square. Similar, all the data, all the coefficients can be easily determined, and these constant terms can also be determined. So this is a system of linear equations. So if you remember from the last section, which was about solving a system of linear equations, you used Gaussian elimination, also Gauss-Jordan method or the Gauss-Seidel method. So all of those methods can be applied here to solve these system of equation. So this is actually an application of the methods that we learned in the last section about Gaussian elimination or Gauss-Jordan methods and other methods as well. Similar to the linear regression, we can determine a standard error, which actually denotes how much the fitted line deviates from the true values. So that is SYX. So this is denoted as root over SR divided by n minus m plus 1. Okay, SR is the error term, summation of the error square terms, and n is the number of data points, and m plus 1, we have, what is the m plus 1? What is denoted by m plus 1? M plus 1 is the data derived coefficients, A0, A1, AM, and these were used to compute the term SR. So we have actually lost m plus 1 degrees of freedom. Okay, that's the main term here, m plus 1. So let's look at an example that will be very much clear about, that will make you clear about the polynomial regression. So we look at this example here. We are given some of the data points, xi is 0 to 5, and we are given the corresponding yi values. So we need to fit a second order polynomial on these data points. Okay, so what we need to do, we need to solve these three equations to get the values of a0, a1, and a2. To get the values of a1, a0, and a2, we need to determine these coefficients term. That means n, summation of xi, summation of xi cube, and all of these terms. So we can determine these terms from this table. For example, m is equal to 2. Why is m equal to 2? There are three equations here. Okay, a0, a1, and a2. And that means there are 3 degrees of freedom, but we have already lost 1 degrees of freedom, and that makes the term m equal to 2. Okay, n is the number of data points, 0 to 5. That means total 6 data points. Then we determine the summation of xi, that means sum over all of the x terms, summation of yi, sum over all of the yi terms, summation of xi to the power 4, that means we take the fourth order of each of the data points and then sum over all of them. So we can get the value, which is 979. Similarly, we can get all of these terms from this table only. Okay, so what are the results? These are the results actually. So m equal to 2, n equal to 6. Similarly, we can determine all of these data points and all of these coefficient terms. And once we do those, we have already calculated all of the coefficient term. Now we can just simply put those values into these three equations and get three simpler equations, a system of three equations with three unknowns, with knowing all of the coefficients and all of the constant terms. So we can easily apply the Gaussian elimination or Gauss-Jordan method or Kramer's rule, whatever you like. Okay, so we have these three system of equation. We can easily apply those solving techniques of system of linear equations from the last section, which is we can apply Gauss-Jordan or Gauss-Seidel or Kramer's rule, and we can solve these three unknown terms, a0, a1, and a2. So once we do that, we will get a simpler polynomial regression, a second order regression. This is a0, 2.47857, and a1 equal to 2.35929, and a2 equal to 1.86071. So this is the fitted polynomial regression line. Okay, so let's determine how good that fitted line was. So we can easily determine the error square terms. That means we can determine the summation of all of the error square terms. So we can determine those from the true values and the fitted values. The true values are denoted by yi, which is given in the table in the last slide, and the fitted lines are determined from the fitted data points are actually determined from the least square regression line. So for example, if we want to determine the approximate value of xi at xi equal to, say for example, 2, so we just put xi equal to 2 into the polynomial regression line, into the fitted polynomial regression line, and we can determine the yi approximate. So if we just take the difference between the yi and the yi approximate and take the square term, we will get the error square term. So all of these, for all of these data points, we can determine the error square terms, and then if we take the summation, we will get the SR term. That means the sum over all the squared error terms. That is 3.74657. Okay. So once we do that, we know the SR term, and we are given the N term, which is 6, and the degrees of freedom available is 6 minus 2, which is 4, and then 4 minus 1 equal to 3. So that makes the SYX, which is the standard error estimate based on the regression polynomial, which is 1.12. So this is a good fit actually. So let's move on to the next slide, which says about the multiple linear least square regression. So we have already said in multiple linear regression, we are just given two individual independent variables. That means our function y depends on two different variables, say for example x1 and x2. So this is a multiple linear regression where we have two independent variables. Okay. So for this case, we can denote the equation of regression line, that means the whole equation, which is y equal to a0 plus a1 x1 plus a2 x2 plus c. So this is a multiple regression line with a linear order. That means we are just fitting a first order regression line with two independent variables. We are not fitting a polynomial regression line, rather we are fitting a linear regression line. If we want to fit a polynomial multiple regression line, we would have a second order term. That means a 3x1 square plus a 4x2 square. These terms would be there, so the equation would be much more complex. So if you want to do that, you can do that at your home. So for now we are just considering the linear regression. So y equal to a0 plus a1 x1 plus a2 x2. So we are just given two independent variables, and for that two independent variables we can fit a linear line. So actually we are not fitting a line here, since we are given two independent independent variables. We are actually fitting a plane. Okay, a plane. That's what this equation means. a0 plus a1 x1 plus a2 x2. This is a equation of a plane. So y equal to, y is the individual true data points that we are given, and e is the error term. So if we just subtract y, subtract the linear regression plane actually, y from the y, we can get the error term. So e equal y minus the linear regression plane. Okay. So once we do that, we are actually finding a plane, a fitted plane. So these data points are actually situated over or below the fitted plane. So this is the fitted plane, this one, and throw the data points in the x1 x2 plane. Okay. So we need to find the coefficients that actually determine the best fit plane. So what coefficients we are looking for? We need to determine a0, a1 and a2. So if we determine these 3 points, we can get the best plane actually. So to get that best plane, we need to minimize the least square error. So to get the least square error, we just subtract the best fitted line from the true value. That means y minus this best fitted line, which is denoted here, yi minus a0 minus a1 x0 x1i minus a2 x2i. So these are the individual data points error. So we take the square, then we can get the summation of overall of the data points, and then we can just determine the SR term. So what we want to do, we want to minimize this SR term. So we need to differentiate this SR with respect to A0, A1 and A2. So once we do that, we will get similar three equations, and we can easily solve those three equations like before that we determined in the previous cases. That means for linear regression or polynomial regression. So the procedure is all similar in all of the cases. We just determine the error square term, and then we differentiate the error with respect to the independent parameters of the fitted line, and then we just equate those equations equal to 0, and then just similar algebraic manipulation. We can just have three equations with three unknowns, a0, a1 and a2, and then we can solve those. So the procedure is same for all of the regression methods. So let's look at an example here. So we are given two independent variable points here, 0, 0 to 1, 2.52. So all of these independent pairs, we are given a dependent value 5, 10, 9, 0, 3. So y is the dependent value, and x1 and x2, these are the independent values. So we need to fit a regression plane through these data points. So we need to solve these three equations that we just determined in the previous slide. So to determine, we have three equations and three unknowns. So we can easily determine these 3 points. So we just need to find out these coefficients and these constant terms. So we can easily determine those from this table. Okay, so I am not showing you the whole calculation, you can do that at your home. So I am just summarizing the results that we just got from the analysis of the problem. So these are the y variables, these are the x1 variable, this column denotes the x2 variable. So we can easily determine the x1 square term, x2 square term, x1 x2, x1 times y, and then x2 times y, and then in the final row we are just taking the summation over all of these columns. So these are the variables, these are the coefficient and the constant terms that we need to put on into the equations. Okay, so once we do that, we can get the coefficients something like this. This is the coefficient matrix and this is the constant matrix. So we can easily solve this system with Gauss-Jordan method or Gaussian elimination. So once we do that, we get the results something like this: a0 equal to 5, a1 equal to 4, and a2 equal to -3. So these are the characteristic parameters of the fitted linear regression plane. Okay, so these are the that was actually the multiple linear least square regression. So we can easily extend our case for multiple variables. So for example, we are not given two independent variables, let's say we are given m independent variables. So we can easily manipulate the main equation into this extended form. That means a0 plus a1 x1 plus a2 x2 plus a3 x3 up to am xm. So this is the generalized linear square regression, least square regression equation. So we are given here multiple greater than two independent variables. So we cannot just say what we are fitting here, because the dimension is bigger than the 3. So if the dimension bigger than the 3, we cannot just say we are fitting a line or we are fitting a plane or we are fitting a volume. So we cannot just imagine what it would look like for the cases of dimension greater than 3. So okay, so this is the generalized equation. This is just for your reference. So if we just want to fit a regression equation into the data points, we just need to find out the error term. So that error term can be easily determined by subtracting the fitted line from the true values. And for the general purpose, we can just determine the standard error of the fitted line, which is SR divided by n minus m plus 1. So this is the generalized equation of the standard error. Now let's move on to the nonlinear regression. That means we are just given a function that is not linear. So there are many cases in engineering and in your study or research that you would like to fit a nonlinear models. Okay, non-linear models to the data points. So these are not just linear regression, so these are non-linear regression. So we are just fitting some other types of curves that are not linear. For example, we are given this function here, f of x equal to a naught into 1 minus e to the power minus a1x plus e. So this is the fitted regression model, a naught into 1 minus exponential of minus a1x, and this is the fitted regression model, and e is the arrow term. Here e is the arrow term. So that makes this the nonlinear regression. But for nonlinear regression, the equation can be easily determined using Gauss-Newton method. Okay, so but the Gauss-Newton method, this is not the same as the linear regression, so we need to get to other methods like Gauss-Newton method for nonlinear regression. So but the Gauss-Newton method has some shortcomings. That means there are some limitations of this method. First of all, it may converge very slowly. Second, it oscillates very widely. As a result, the functional data points oscillates very much frequently than the linear regression cases, and the equation continuously changes direction, so it may not converge at all. So that's the third pitfall here, that the method might not converge at all. So these are the three shortcomings of the Gauss-Newton method. So be careful of that. So we are not just going to the details of the Gauss-Newton method. That's just for your reference. You can go through the Gauss-Newton method if you want to fit a nonlinear regression lines through your data points. So that's up to you. So we are not just covering that Gauss-Newton method here. We are just confining ourselves to the linear regression cases, linear and polynomial. So we have just reached the end of this lesson. I am just informing you that I have just attached the MATLAB course of linear regression, polynomial regression and multiple linear regression with this video. So please go through the MATLAB code and go through each of the line of the course so that you can understand how the methods are actually implemented in computer. So in the next lesson, we are just going to learn about another type of curve fitting, which is named as interpolation. And we are just going to know about the differences between the interpolation and regression. So till then, thank you so much.